All right, let's see if the captions are working. Yes, they are. Good. Okay, share the screen. So let's see here. Last time we talked about radian measure. We talked about coterminal angles. We talked about finding the angle theta star for a given angle. And we talked about the reference angle for a given angle. I think that was it, if I'm remembering correctly. What questions do folks have? Yes. Sure. Starting with an angle in radians or degrees? Okay. So, for finding the angle theta star, that in degrees is between 0 and 360 degrees, or in radians is between 0 and 2 pi radians. The basic idea is to add or subtract enough groups of one rotation. So 360 degrees or 2 pi radians. From theta. So you could just do it one at a time. If you have a positive big angle, subtract 360 degrees, get the answer. If that's not less than 360, then you subtract another group of 360, etc. But you can save yourself a little bit of time is to first to estimate the number of groups that you will need to add or subtract by either taking theta divided by 360 degrees or theta divided by 2 pi radians. Good morning. Alejandro, right? Okay. So if we have, say, how about 65 pi over 12 radians. So there's a couple of ways to find that estimated integer number of times. We're going to have to subtract or add a negative amount of 2 pi radians. Method one is to start by taking 65 pi divided by 12 radians and dividing by 2 pi radians. It makes it a little easier if we get a common denominator. Because then to do the division, when we multiply by the reciprocal, that's equivalent to taking 65 and dividing by 24. So that's more than 2 and less than 3. So to figure out the angle we're looking for then, we're going to need to take the angle that we started with and we're going to essentially subtract 2 groups of 24 pi over 12 radians. So in other words, we're adding negative 2 groups of 24 pi radians. So that would be negative 48 pi over 12 radians. And let's see, when we subtract, we get 17 pi over 12 radians. And that's a positive number. And it's less than 2 pi, less than 24 pi over 12. So if we had done, when we did 65 divided by 24, if we had done that pencil and paper long division, 2 groups of 24 is 48, and there's 17 left over. And that 17 is this same numerator here now. If the angle we had started with had been negative 65 pi over 12 radians, we would do the same kind of work, and of course, if we take negative 65 and divide by 24, our answer is negative 2 point something. In other words, it would be negative 2 and 17/24. Oops, put the negative in the wrong place though. There we go. And the 2 groups of 1 complete rotation, 2 pi radians. So 2 groups of 24 pi over 12 is 48 pi over 12 again, like before. But if I'm starting with negative 65 and I add 48, my answer is still negative. So I'm going to have to add a 3rd group of 2 pi radians. So negative 65 pi over 12 radians plus 3 groups of 24 pi over 12 radians. 3 groups of 24 is 72. So if I have negative 65 pi over 12 radians, and I add positive 72 pi over 12 radians, now my answer is going to be positive. And just an arithmetic fact to notice, this 7, which is sort of like a remainder. And in the previous problem, the 17, which was a remainder, if you add them together, 17 and 7, you get 24. So 1 whole group of 24. So if we were to be real formal about it, the number K is the opposite of the floor function of theta divided by 2 pi radians, if the problem is in radians or in degrees, we divide by 360 degrees. So the floor of positive 2 and 17/24 is 2, but the floor of negative 2 and 17/24 is -3. So the integer that is equal to or just less than the number, that's what the floor function does. You may or may not have seen that before. There's actually a notation for that, but you don't need to know that. So in the first example, we had to add negative 2 groups of 360. So in other words, we had to subtract 2 groups of 2 pi. And in the second time, we had to actually add 3 groups of 2 pi. Well, the opposite of a negative number is positive. So does that help? Yep. Okay. What other questions do folks have? So we know that, like, if we're driving down the highway, and if we're traveling at a constant rate of speed for a certain amount of time, then the distance we travel is what we get when we multiply them together. So if I'm driving on the highway and I set my cruise control at 65 miles an hour and I travel for exactly 3 hours, that's exactly 195 miles along the road. But another way of writing that same equation is that the rate of travel is distance divided by time. So if I know I traveled 195 miles in 3 hours, if I was traveling uniformly, if my speed was constant, then my speed was always 65 miles an hour. Uniform motion means the rate R is constant. We can also talk about what's called your average rate, your average speed. So suppose the thing moving, whatever it is, so for now, let's suppose that the motion is always in the positive direction. Then we don't have to make a distinction between speed and velocity. Those of you that have had a little bit of physics. And in physics, sometimes they write T initial. So the initial time and the final time. And then we have position initial and position final. And then we will say that the average velocity from the initial time to the final time is P final minus P initial over time final minus time initial. And that's the ratio of the corresponding differences of two measurements. That's a slope. Just like y sub 2 minus y sub 1 over x sub 2 minus x sub 1. It's exactly the same formula, just in a physics context. And sometimes in physics, then they'll write delta P over delta T where that's a capital delta in the Greek alphabet, but in this context, delta means the change in. So all of which is to say that if you have a line and its slope y sub 2 minus y sub 1 over x sub 2 minus x sub 1, a lot of times physics teachers will say change in y over change in x, like that. Everybody with me so far? Right? Okay. Often the initial time is 0 and the initial position is also 0. In which case, the average velocity just becomes P final divided by T final, which is often written as just P over T, or D over T, distance divided by time. So on the one hand, uniform motion implies that the speed was always the constant. Cruise control was on. We might not know if it was set at 65 miles an hour or 30 miles an hour, but car or the vehicle, whatever, was always moving at that constant speed. If we allow for the speed to change over time, then instead of saying the speed, the actual speed is distance divided by time, we say the average speed is the change in the distance divided by the change in time. Okay, so I'm going to just let that sit in the background for a minute. Okay, suppose we have a circle. And we might as well call the radius little r. And there's a point P on the circle. And we might as well call the center of the circle capital O. So here's our circle. We have point O. I'm going to call this point point A. Or, yes, but I was going to name this point two different ways, but I think I'm going to change my mind back. And now there are, I don't know what to call them, two situations, two scenarios. One is the circle is spinning around its center, or the circle is rolling along a flat surface. So either it's just spinning right here, round and round and round and round, or we're riding our bike and it's going like this. Make sense? Okay. In either case, whichever way you think about it, once we turn the video on and we see the circle start spinning, point P is going to be spinning around the circle, right? There are two ways to measure to answer the question, how far does point P move? We can ask how far, literally, does point P move? And we can ask through which central angle does point P spin? Okay. So let's take my same circle and suppose the circle only spins a little bit. And suppose P ends up here So suppose this is sort of P initial. And this is P final. And suppose the amount of spin was that angle. Just the first time around, just to make the picture easier. So this S equals the arc length equals the distance traveled and the theta equals the angle through which the circle was rotated. Can't spell. So P initial, that's at time T initial, which we'll say that that's when we're going to start the clock. And then the circle spun a little bit and ended up over here. And so P final happened at time final. So and let's suppose the speed of rotation is constant. So again, uniform motion, but it's the speed of rotation is constant. Then the linear speed, or more precise, if the speed wasn't constant, then it would be average speed. Okay? But the linear speed, which we'll call V for velocity, even though in this context everything is going to be positive, so it's speed. That's going to be the change in position divided by the change in time. Which technically well, let's just put it this way. So that's going to be S divided by T, or T final really, but if T initial is 0, then T final minus T initial is T final. So we can just call it time. Likewise, when time is 0, the arc length is 0. The initial length, the initial distance that this point traveled is 0 units. And then at after a certain amount of time, we end up there. And then there's this distance that it's traveled from the initial point. But if we lay down our tape measure on the circle so that this is 0 centimeters or 0 meters or 0 inches, whatever units we're using, then P final minus P initial is this number S. But then we also have angular speed, which we use a lowercase omega which sort of looks like a Latin W. Uppercase looks like this. But it's kind of curvy instead of straight sides, like in the Latin lowercase w, which is really a double V. But we call it a W because U's and V's used to be the same long time ago. So this is going to be the change in the angle divided by the change in the time. And so theta divided by T. So if we measure time starting at T equals 0, if we measure the angle starting at theta equals 0, and if we measure the arc length starting at S equals 0, then change in position divided by change in time, S final minus S initial is just S final, and we just say S. So technically, right, the linear speed is change in position divided by change in time, but we often just write S over T instead of change in S over change in T. And angular speed is the change in the angle divided by the change in the time, but we usually just write theta over T. Okay, so far so good on those definitions? So like a snowboarder going down a half pipe, when they get to the top of it, maybe they spin around 3 times in a half a second. So that would be the same as 6 rotations per second, something like that, right? That would be an angular speed. Okay. So we can solve many problems, answer many questions. Involving both linear speed and angular speed by remembering that in every one complete rotation or revolution. So physicists make a distinction between these two things, a rotation and a revolution. The Earth spins on its axis, which is essentially a north-south line through the center of the Earth, not exactly, but right. And so the Earth is rotating, but the Earth itself is also going around the sun in a nearly, but not quite, circular orbit. And so we say that the Earth revolves around the sun. So if we think of the circle standing still, but point P is moving along the circle, then we can think of that as a rotation, no, as part of a revolution. But if the circle is spinning, then we talk about rotations. But they're sort of the same thing, they're sort of different, but in this case, you don't really have to worry about the distinction between them. Okay. All right. In every complete rotation, the point P travels a distance equal to S equals 1 circumference of the circle and point P travels or determines, or there's some verb I'm missing, something out. My brain is not thinking of the word right now. So let's just say travels through an angle theta equals, and here you can either say 1 revolution or 1 rotation. In other words, 1 revolution in terms of distance is 2 pi r units of length. But in terms of angles, 1 revolution is either 360 degrees or 2 pi radians, which is a measure of spin, an angle. Comments, questions? Sure. And then we use dimensional unit analysis. Unit analysis is a really important concept in math and science. We use it all the time. If you truly understand unit analysis, that gets you about 2/3 of the way through a beginning physics course, like a high school physics course or a first year general ed physics course, not necessarily a physics major first semester course. It gets you about 1/3 of the way through chemistry. It gets you all the way through medical dosage calculations, et cetera, et cetera. Okay, so let's look at a couple of problems. So it was just the state fair. Maybe you went on a Ferris wheel or the merry-go-round or some similar. So if there's a wheel, that means there's a circle involved. So we have a circle. We know the radius is 30 feet. And as it's going around, it takes you 70 seconds for one revolution. So one revolution equals 70 seconds. So what that is telling us is that the angular speed omega is one revolution in every 70 seconds. The second question that's asked is, what is the angular speed in radians per second? So we'll call this question the A part, we'll call this question the B part. So in part B, we were told in the problem that the angular speed is one revolution in every 70 seconds. but we're being asked to answer in radians per second rather than revolutions per second. So everyone understand the question? Okay. So if the angular speed is 1 revolution per second, we're going to play the multiply by 1 game. And we need to get rid of revolutions and go to radians. Right now, revolutions is in the numerator. So we're going to need revolutions in the denominator in our name for 1 and radians in the numerator. And we know that in 1 complete spin, there's 2 pi radians. So the exact answer is 2 pi over 70 radians per second, which these days we're supposed to abbreviate seconds with just the S, but my S's look like 5s, and so I'm not going to do that. We can approximate that if we want to. It doesn't tell us whether to give the exact answer or not, so I would probably stop there. Or actually, let's see, we could simplify that, couldn't we? So that would be pi over 35 radians per second. And you can write that way as 2 fractions multiplied together, or you can write it as 1 fraction. Sometimes, hang on a second, sometimes in physics, they'll write pi over 35 radians, and then they'll put seconds to the negative first power. Because a negative exponent means take the reciprocal, right? So.
Over 35 is the fraction and then wait towards radians 3 seconds after.
You could. So you could write pi over 35 radians per second. Of course, that's the exact answer. If we want the decimal answer, then we can get our calculator out. And if we know we want the decimal answer, we wouldn't even have needed to simplify the fraction. So we can either type pi divided by 35, or we can type 2 pi divided by 70. Whenever you have an operation inside a fraction, it's always best, particularly when you're in classic mode, if you tell the calculator exactly what the numerator is and what the denominator is. So I would use a set of parentheses 2 pi divided by 70. There's only one number in the denominator. There aren't any operations, so I don't need parentheses in the denominator. In this particular fraction, the only operation inside the fraction is in the numerator, not the denominator. And the only operation is multiplication. If both of those things are true, then I don't need the parentheses. I'm going to get the same decimal result. So you could type it in either of those ways. Or if you like math print mode, so now I'm in math print mode, you can get a fraction to look like a fraction by typing alpha F1. And then there are 4 submenus that you can use your left and right arrow keys. We want a fraction. We don't want to use mixed numbers. So we're not gonna, it's not gonna be 2 or 3. So we're gonna choose choice 1. Now my fraction looks like a fraction. And I can type 2 pi. And then the right arrow will move me to the denominator. I can type 70. The right arrow again will go to the right of the fraction. And then I can press enter and I'll get the decimal point. So math print mode is nice for that reason, because you can make a fraction look like a fraction. I spend a lot of time at a regular keyboard or just on my phone where I don't have specialized software that can make a fraction look like a fraction. So I tend to use classic mode. Besides, I'm old, so I learned to use computers before any of them had ways of writing mathematics nicely. And they didn't tell us what to round off to. So since they didn't tell us, the assumption is they want the exact answer. But if we really do want an approximation in this class, I will always tell you round to so many decimal places. And if for some reason I forget, then just do something reasonable. So 70 has only 2 digits in it. It might just be that the 7 is the only significant digit, or it might be the 7 and the 0 is significant. So we probably only want to keep 2 or 3 digits in our answer. If you kept 3 decimal places, that would be okay. Notice to 3 decimal places, it would be 0.090 radians per second. For the rest of your life, if you have a decimal number that's a proper fraction, or even if it's irrational, like in this case, If the number is between 0 and 1, always write the 0 in front of the decimal point. It's just a rule that was only starting to become a rule when you folks were in like elementary school. Okay, so your previous teachers may not have insisted on that, but I'm going to, because your science professors are going to, among other things. And the reason is it makes it clear that the decimal point really is a decimal point and not just a mark on the paper, right? If we were giving somebody medicine, we wouldn't want to give them 90 milligrams of medicine if we were supposed to give them 90 over 1,000 milligrams of medicine, right? So that's the reason. If the directions say round to 3 decimal places, then your answer has to have exactly 3 decimal places. So it would be incorrect to write 0.09 radians per second if I asked for 3 decimal places. Yes, that 8 would still round up to a 9, but I need to have that 3rd decimal place. Okay, so that part of the question was not as difficult. There was just one unit conversion we had to do. We were told the angular speed essentially, but then we just had to convert units from revolutions to seconds to radians per second by remembering that in every one spin, in every one rotation, in every one revolution, the point on the circle moves through an angle of 2 pi radians. But this question also asks us for the linear speed. And it wants the answer in feet per second. And what we know is the radius was 30 feet. And we knew that 1 revolution took 70 seconds. When the question is asking you for a speed or a velocity, that's always a rate. It's always a fraction, some kind of units divided by units of time. Usually time, doesn't have to be time, but usually is time. If they are asking for a speed, you need to start with a speed. If they are asking for a distance, you need to start with a distance. If they are asking for an angle, you need to start with an angle. Okay? So they're asking for a speed. We need to start with some sort of speed. But the only speed they gave us was that 1 revolution is the same thing as 70 seconds. But what we need to know, and notice that's still an angular speed, and I'm trying to figure out a linear speed. I'm going to use a similar unit conversion with 1 revolution in the denominator. But in terms of distance instead of angle, the car on the Ferris wheel is going to travel a distance of 2 pi times the radius. In other words, 1 circumference's worth of distance. So we get 60 pi over 70 feet per second. If we want the exact answer, we can simplify that to 6 pi over 7 feet per second. And if we want the decimal answer, let's see, hang on a second. 6 times pi is 3-ish. So 6 times 3-ish is 18-ish. Divided by 7 is between 2 and 3. So hopefully when we type in our answer, we get a number between 2 and 3, and we do, so that seems reasonable. So that would be 2.693 feet per second to 3 decimal places. You had a comment.
Yeah. Would it be multiplied by 30 or by 6? Because 30 would be the radius.
Yes, and then I have the 2. So 2 pi r, right? Right, so circumference equals 2 times pi times r. Yep. But you are correct. We're actually multiplying pi by 60. So notice that we converted an angular speed to a linear speed. But we did it just by looking at the units. We didn't have to memorize anything that we didn't already know. Make sense so far? Your authors, I think it's Michael and his grandfather, Michael. Your authors give you a formula for converting between angular speed and linear speed. That's a nice little formula. But 1, I don't have room in my brain to remember more things. And 2, that formula only works in a special case. Unit conversion always works. Why learn something you don't need to know? Does that philosophy make a little bit of sense to you anyways? If you're really good at memorizing things, which sometimes math students are, because we were really fast at memorizing our multiplication tables in 3rd grade compared to some of our classmates, maybe not, but maybe. Or memorizing phone numbers or social security numbers and all that stuff, right? So maybe you're good at memorizing formulas. Okay. But for the particular formula that your author uses, you also have to memorize that it's a special case of something. And so it comes with a condition attached to it, which to me, that's harder. Suppose I add a question to this. how far will a car on the Ferris wheel travel in 5 minutes? When the question is how far, what's the physics word for how far? Distance, right? And what kind of units might distance be measured in? Miles. What else? Feet. What else? Inches. Kilometers. Micrometers, micrometers, meters, right? Distance, okay? So are they asking us for an amount of something or a comparison of two things, a rate? Like something per something. Well, if they're asking us for a distance, the units are something like meters or miles or feet or whatever, not feet per second, not pounds of pressure per cubic meter, per square meter, the area probably. Right? Not a rate, an amount. So distance is an amount, not a rate. So we need to start with an amount, not a rate. So in the previous two problems, we started with 1 revolution per 70 seconds. That was a rate. We need to start with an amount. And the facts that we know is that the radius is 30 feet, that 1 revolution takes 70 seconds in this particular problem. And we know that the time is 5 minutes. And the question says, what is the distance? What is that amount when the time is 5 minutes? Which is also an amount. So we're going to start with the 5 minutes. And we need to convert that to a distance. Yep. So we're going to use that. But in the angular speed that we were given, the units were 1 revolution takes 70 seconds. So first, we're going to need to convert from minutes to seconds. And hopefully that's a conversion we know, and if we don't know, we could look it up, but 60 seconds is 1 minute. So we still have an amount because the minutes are going to divide out. We still have an amount of time because the units are still seconds. Somehow we need to get to amounts of distance. Well, the only thing we know about seconds for this particular problem is that 70 seconds is the amount of time it takes for one revolution. So if we want to get rid of seconds, which were in the numerator, we need to have seconds in the denominator, and then we can have revolutions in the numerator. And in this particular problem, one revolution is 70 seconds. And the key idea is that in one revolution, the car is going to travel one circumference's worth of distance. So 2 pi times 30, and those units are feet. And now we have converted time to distance. If you want to, you can just sort of write all of the factors in one fraction so you can see them. I might put the 30 first and then the pi. And our answer is in feet, which is in the numerator, which we could figure out the fraction part if we wanted to, or we can type it out. So this is exactly, but not simplified. Because there's certainly a common factor of 10. That's the only common factor. Well, 5 times 2 is 10, so I can actually do this one in my head. So I'm going to have 60 times 30 is 1800 pi over 7 feet. And that's exact and simplified. And then I can use my calculator to get a decimal answer. Again, the only operation in my fraction is in the numerator, and it's a multiplication. So the calculator will do the multiplication first. And probably in this situation, we wouldn't round to 3 decimal places. Maybe we'd round to the nearest whole number. Because that already has 3 digits in it. But the directions will tell you. Let's pretend we haven't done the problem we just did. If we already have done the problem we just did, we could use that answer to help us figure out this answer. But we're going to start the same way, right? So the facts that we know is that the radius is 30 feet. We know that 1 revolution takes 70 seconds. Those 2 facts are only for this problem. And we know that the total time traveled is 5 minutes, and that's also only for this problem. The question is, what happens, blah, 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 in 5 minutes? So again, I'm going to start with the 5 minutes. Again, I'm going to need to convert minutes to seconds. So that's still a time, still in seconds. And we know 70 seconds. In 70 seconds, the car moves through, completes 1 complete rotation or 1 revolution. And we know that in 1 revolution, the car is going to move through a distance of 2 times pi times 30 feet. So all of that so far is exactly the same as the previous problem. But now we have the additional computation or the additional conversion that we need to get rid of feet and go to miles. And that number I do have memorized. I don't know why, but once I learned it, I always remembered it. I don't have to look it up. So since we know we want the answer to the nearest whole number, again, if it helps, you can kind of clean it up a little bit so you can see what you're doing. There's an operation in the denominator. So we need to use parentheses. But we don't need to get the exact answer in simplified form because the question didn't ask us for that. It asked us to round the answer to the nearest whole number. We can simplify the fraction if we want to, but we don't need to. In the numerator, the only operation is multiplication, not addition or subtraction. So we don't have to put the numerator in parentheses if we're in classic mode. We can if we want to. But if we're in classic mode or if we're in math print mode, but we didn't type alpha F1, we have to tell the calculator to do the multiplication in the denominator before it does the division. I learned that one the hard way when I was a student. Okay, so to the nearest whole number, that's gonna be 0. So let's say, let me change the question to the nearest, just to make it interesting. How about the nearest hundredth? Spit on your neighbor. 100th of a mile. So that would be 2 decimal places instead of 0 decimal places. So that would be 0.15 miles. I could change the question again. And ask you to round to the nearest millimeter. It's kind of a ridiculous question, but it serves the point. So we're going to start the same way. 5 minutes is the same thing as 5 minutes divided by 1 multiplied by a bunch of other ones. Again, 1 minute is 60 seconds. We need this second fraction to have the minutes in the denominator because they were in the numerator. And we can get rid of seconds and go to revolutions because the angular speed was given to us. 1 revolution per second. So now we're in revolutions, but we want a distance. So in every 1 revolution, the car travels 2 times pi times the radius, 30 feet, units of distance. And 1 foot is the same thing as 12 inches, still in the customary units. But the customary units have been redefined so that 2.54 centimeters is now the definition of 1 inch. And some of you are able to go directly from centimeters to millimeters. But in general, with the metric system, 100 centi whatevers is one of the whatevers. So meters or liters or kilograms. And 1 meter is the same thing as 1,000 millimeters. Now, whenever we are converting from customary units to metric units, there can be some round off error, except for that this one is exact. 2.54 centimeters is 1 inch. let's see what we get here if we type this in. So this time I'm going to use parentheses just to be sure. So 5 times 60 times 2 times pi times 30 times 12 times 2.54 times 1,000, and the numerator divided by, start the denominator, I've got 70 times 100 in the denominator. This is the easiest way to type it in classic mode, as long as your numbers stay within the numbers your calculator knows. Otherwise, we could type, say, 5 divided by 1 in parentheses times 60 divided by 1 in parentheses. And of course, the dividing by 1, I wouldn't have to type, times the 1 divided by the 70. And see, now, even if when I multiply the first two numbers together, that's a relatively big number, it's still smallish for a machine. Well, it's only 300, right? But if it was 3 trillion or 3 quadrillion, your calculator doesn't know numbers that big, okay? So by dividing by 70, that makes the number smaller again, right? So I'm lessening the chance of having an overflow situation, of a number that is too big that my calculator doesn't know what that number is. And likewise, I'm simultaneously avoiding the possibility of having an underflow, a number that's too close to 0 that the calculator doesn't know what it is. So this is just an alternate way of typing it in that is mathematically equivalent but computationally better for the machine. And my calculator knows implied multiplication, so I wouldn't need that multiplication sign right there if I didn't want it. It's important to know that not only are your numbers correct, but and do you know how to type it into your machine so that you will get the right answer? But it's also important to know computationally, if you are programming a machine that's going to do these kinds of calculations, but you are flying to Mars, not riding a Ferris wheel for 5 minutes, you need to have a machine that is capable of really big numbers and really small numbers. And this is an example of the type of problem where if you type it one way, the calculator will, through no fault of its own, will either give you the wrong answer or say, I don't know. But if you type it the other way, the calculator does know the answer and gives you the correct answer. So my two answers turn out to be the same. So that branch of mathematics and computer science is called, and I just lost the word for it. Numerical analysis. All I could think of was number theory, which is starts the same, but it's different. So numerical analysis, how to ensure that the computation, that your computational machine gives you the answer you're expecting it to give you, the correct answer, without overflowing or underflowing, and gives you the answer in a reasonable amount of time. We've all sat there and waited for things to load on our computer, right? So we know that some computations take longer than others. Sometimes it's the physical machine doing the computation, and on the internet, it's the communication through the radio waves maybe, or whatever. So what do I have here? 246,229 millimeters. Someone else, because we're expecting these distances to be large, you know, with several feet, someone else may happen to know a different conversion, maybe because they drive a lot between here and Canada or other foreign countries. And they know that 5,280 feet is 1 mile. And 8 kilometers is approximately 5 miles. This one is not an exact conversion though, but it's a nice one to know when you're calculating the distances. And then we don't, well, if we wanted millimeters, then we would say 1 kilometer is 1,000 meters, and 1 meter is 1,000 millimeters. So let's see how our answer compares this time. See if we get the same answer or a different answer. So my first several fractions were the same. Oops. Yeah, okay. So right here, instead of 12 inches is 1 foot, I have 1 mile. 1 mile is 5,280 feet. And 8 kilometers is about 5 miles. And then there's 1,000, 3 zeros, meters in every kilometer. And there's 1,000 millimeters in every meter. So to the nearest whole number, we have the same answer, which, by the way, also, instead of using commas these days, we're supposed to use spaces. Oh, no, it's a slightly different answer, isn't it? I'm getting 244,799.
Not confusing.
No, because you see, in half of the countries in the world, they use a period for the decimal point and they use a comma for the groups of 3 in the whole number part. But in the other half of the world, they use a comma for the decimal point and a period for the groups of 3, which is confusing, right? It's just completely backwards. So the countries of the world, the scientists of the world, have agreed to agree that everybody should use the period for the decimal point and spaces for the group of 3, including in the decimal part of the number. So if this number was typed in a newspaper in this country, there wouldn't be a space and there would be a comma if it was for the everyday reader. But in maybe some Latin American country, it would be 244.799. But if it's in a scientific journal, it's going to be 244 space 799. It's about 20 years old, but yeah, if you look, it's a thing. I can even find the prefix. I don't even know what the letters stand for, is ISO. It's the scientific agreement among people. We could probably look on Wikipedia for the whatever. Anyway, so no, you know, we were off. Our answer's different than it was before, right? In fact, we don't even agree to 2 digits. But that's because this one approximation, because we converted from customary units to metric units, usually those aren't exact. So notice, if we only kept 2 digits the first time, two significant digits, this would be 2.5 times 10 to the 3/4 millimeters. Whereas this one would be 2.4 times 10 to the 5th millimeters. And that's how your science and engineering people are going to want you to write your answer. So that's a 10% error compared to each other, right? So if we were flying a spaceship to the moon, to Mars, and if we were measuring in millimeters, probably 2 significant figures, when this exponent is big, that's not going to be enough accuracy. And we need to tell the spaceship when to start slowing down as it enters the gravity of Mars. And right now there's what, 2 or 3 rovers rolling around Mars doing their thing, collecting information. But before that one, there was one that crashed into Mars because it was going too fast and it didn't slow down early enough because of this kind of error. because they didn't keep enough significant figures in all of their calculations. And so they were going too fast for too long, and therefore they went too far. And the machine crashed and disintegrated into Mars. But I just wanted to point out that this idea of unit conversion, sometimes we have to convert within systems, inches, feet, and miles, seconds, minutes, and hours, days, weeks, years. Sometimes we have to convert between customary units and metric units. Whenever we convert between customary and metric, there is an amount of error built into that, which is also an additional problem that Mars lander had a problem with, is because there was one, let's just say, subroutine that was using customary units for some reason, and the other one was using metric, and so that added to the round-off error problem. I could ask a fourth question, which is really what, the sixth question now? Through what angle will a car travel in 5 minutes and round to the nearest tenth of a radian? So again, it's important to know what the question is asking. It's asking for an angle, which is an amount, not a rate. And again, the facts that we have are the radius is 30 feet. One revolution takes 70 seconds. And the object is going to travel for 5 minutes. And we're going to, the angular speed is going to stay constant. So again, we want an amount. We need to start with an amount. You usually don't start with the radius unless you're just converting the radius itself from feet to inches or whatever, or you're converting the radius to the diameter, a distance to a distance, right? So one of these is essentially a rate. Two of them are amounts, but I'm probably not going to start with the radius, so I'm going to start with the time. So again, I'm going to start with my 5 minutes. 5 minutes is 5 minutes over 1. And again, I need to go to seconds. 60 seconds is 1 minute. And I know that in this problem, in every 70 seconds, which I'll put in the denominator so that it divides out with the 60, the object travels through 1 revolution. And then in this case, I need to change a 1 revolution into an angle in radians. And 1 revolution is 2 pi radians. And I'd like to write RAD or spell out radians. Otherwise, I get confused between the measure of an angle and the radius of a circle. So what did I say? Nearest 10th this time? So 5 divided by 1 times 60 divided by 1 times 1 divided by 70, which if there's addition in my numerator or my denominator, then I can't break it apart as these separate fractions. I would have to type the numerator in parentheses and type the denominator in parentheses. So to the nearest 10th, that's 26.9. Radians. And of course, I could ask the same question, but not in radians. I could ask it in degrees. And if I was really mean, I could ask you to do it to the nearest second. So you'd have to convert your decimal degrees to degrees, minutes, and seconds. So the only difference now is that my last fraction, instead of 2 pi radians, is going to be 360 degrees in the numerator. So 1,542.9 degrees. All right, I had a quiz to give you, but we don't have enough time right now. Maybe what I'll do is I'll give that as a take-home quiz this time, but I want to see if we can find another problem here. I'll pick an even numbered problem. So when you put a CD-ROM or a Blu-ray or a DVD, it spins, or a record player, right, with an album. Sometimes it spins at a constant rate, sometimes the rate changes depending on what the computer is trying to do. Notice that this problem there's a maximum omega of 10,000 revolutions per minute, RPMs. But the disk is actually spinning at 8,000. Revolutions. Per minute. So in this problem, that 10,000 revolutions per minute is extraneous information. Also, the diameter of the disk itself is 12 centimeters. But the point itself that the question is about the point is 4 centimeters from the center. So the point's radius is 4 centimeters. And then the question is, what's the linear speed in kilometers per hour? So that's what we're trying to answer. And a linear speed is a speed, it's a rate. So we're going to start with a rate. Which rate? The rate, the maximum rate, or the rate that the point is actually spinning at during the time of this problem? Well, we're going to use if the disk is actually spinning at 8,000 revolutions per minute, that's the rate we're going to use, not the 10,000. So 8,000 revolutions for every 1 minute is what we're going to start with. Notice that this time we have to convert both the numerator and the denominator. Because instead of revolutions, which in this case is an amount of spin, we want kilometers, which is an amount of distance. And in the denominator, we're starting with an amount of time in minutes, but we want the amount of time in hours. So I would pick one or the other to start with. So do we want to start with the numerator or do we want to start with the denominator? It's up to you. Numerator's in the top, let's start with the numerator. Okay, what do we know about 1 revolution? We know 3 things about 1 revolution. 1 revolution is the same as 360 degrees, which is the same as 2 pi radians. But we also know that the distance an object travels in 1 revolution is 2 times pi times r units of distance. And since we want units of distance in our numerator, kilometers, this numerator of my new fraction here is not going to be 360 degrees. It's not going to be 2 pi radians. It's going to be 2 times pi times 4 centimeters. That's the two hardest things are, what do I start with? And when I am converting one revolution, am I going to use 360 degrees? Am I going to use 2 pi radians? Or am I going to use 2 times pi times the radius's length? Okay, we have centimeters, we want kilometers. 100 centimeters is 1 meter. 1,000 meters is 1 kilometer. So now the numerator is in kilometers, which we want. But the denominator is in minutes, and we want hours. Right now, minutes is in the denominator, so to get rid of them in my new fraction, minutes will have to be in the numerator and then hours in the denominator. And there are 60 minutes in 1 hour. So this minute here divides out with those minutes there. And it didn't tell us what to round to. So it might want the exact answer first, and then maybe they want a decimal answer. If you're ever unsure for something that's going to be graded, make sure you ask me. If I'm not specific, I will either say, find the exact linear speed, or I will say, find the linear speed to the nearest whatever, so many decimal places, or to the nearest whole number, or whatever. Is that clear? Your author isn't clear, right? Since this is an applied problem, not a naked number problem, it's not about an imaginary disk, it's about a physical disk. So probably they're looking for a decimal answer, so whatever we get. So as you leave, this quiz has 2 pages, front and back. Do your own work, and I will trust you to do that. Since you are taking it home, you may use whatever resources are available to you other than other people, or things like homework sites on the web, right? But you can use your notes, you can use your book, and bring this first thing then, whatever, Tuesday, right? Okay. And pretty much all of your homework, practice homework, is going to be problems like we have been doing today with all these unit conversions.
Do we have additional homework for today, or just this?
You'll have additional practice homework. I'll post it on D12.
Okay.
Mhm.
By the way, Alana has COVID. That's why she's sick. So
Oh, who is?
Alana,
Okay,
yeah, so
Thank you.
Assume she'll just take that with her when she comes in next time.
yeah, will you see her or not? Okay,
Well, I'm not gonna go, I don't know where she lives.
Yeah.
I'm not gonna go over here.
right. Yeah, no, I'm gonna, I'll post it too for people that were gone. Your name is very interesting. For lots of different reasons, but your parents may or may not have been old enough to watch Laughing.
I chose my name,
You chose your name?
and my grandparents thought it was funny that I chose that.
Uh-huh.
Yes, I
Yeah.
do know of.
Rowan and
Rowan.
Martin's Laughing, yeah.
Yeah.
So I didn't notice your name the first day, and then the second day you were sitting over there, and I was like, "Huh, I wonder if she told."
Nope.
Yeah,
No,
yeah,
I
that's great.
picked, my own.
Yeah,
Funny enough, it's the type of tree.
really,
Yeah, it's a type of northern ash tree.
really, in this continent?
It's more predominant in Nordic countries. It was very spiritual centered tree in
Cool,
Norse
I like it.
cultures.
Norse.
Just wanted to let you know that I no longer have access to my math lab because my trial went out.
Uh-huh,
So I'll have to wait till I get my financial aid refund to actually afford
okay,
the whole.
okay, yeah, so I will try to remember to print out the problems and then email it to you, so you can at least work on them. Yep. You too.